Okay, I think the recording has started. So, welcome to week 12 live discussion session for the reinforcement learning course. This will be the last tutorial session, which is related to the course material that has been covered so far. And after that, you will have the final end semester exam that you have to give offline. So, if you have any doubts as such, you can always feel free to ask. Otherwise, I have covered till last week. I mean, uh, till week 11, I have. Uh, I mean, in the last discussion session, I had covered everything that was covered till week 12. So if you have no further doubts, I plan to look at the coding or implementation details for reinforcement learning, which will be helpful for you guys. So we can get ahead with that. So it's 6:10. So this class will not take the entire 2 hours, maybe one and a half hours like last time, and then we can uh, end the discussion session for this semester. Okay. So first of all, let me introduce you to something known as OpenAI Gym. Okay. So this is basically Gym is basically a standard API for RL algorithms, and they have some diverse collections of reference environments. And the thing it helps is it sort of streamlines most of the environments that are related for RL usage, and you can simply import or use one of the environment uh, based on the which is you know compatible with respect to gym, and so it's kind of an interface for the environment, okay, so that it makes life easier and in a way standardizes the usage of RL over the entire community, okay. So this is what the environment or the gym interface is all about. We'll look in detail about each aspect. So here you see this is an example of a gym environment. This particular environment is known as a lunar lander. Okay, so you have a spacecraft and you need to land the spacecraft between these two flags. Okay, and the better or the optimal way, the more optimally you land, the higher the reward you get. Okay, so we'll look at each implementation detail of each of it. So first of all, the first thing I do is I go open a collab notebook. Let me share this. So please let me know, okay, if there is some lag or you can't hear me anytime. Okay, I'll just copy paste this. This is the open AI tutorial. Okay. So you can open it side by side and you can get ahead. Okay. Okay. First thing you do is mm, first erase all output. Yeah. So first thing you do is you install Gym in Python. So the first step. Okay, I say open Gym. Okay. So you simply run this command pip install -u gym. Okay. So since I have already installed it, it happened almost immediately, but it need not be. It might take some time. So you look at that. Okay. Next, I do import gym, and in gym, I call this function called gym.make mountain car v0. So this gym interface in Python has lot of inbuilt environments that one can directly use and one can directly pick up from the repository and start using it. Okay. So one such environment is known as mountain car. So this is called mountain car version 0. I'm simply picking that gym repository and I'm doing gym.make and I'm defining my environment to be the mountain car. That's why I did gym.make. So if I were to define what the mountain car environment is, so okay, so this is how the mountain car environment looks like. Okay, so there is a small mountain, and the car has to move till the flag post. Okay, and the car can only accelerate or decelerate in the yeah, it can only accelerate or decelerate, and based on that, it has to go up. So if the car starts from here and tries to pull the accelerator in full throttle and move up, it might not be able to move till the end, till the top of the hill. Okay, so it has to learn that it should swing first, like accelerate, decelerate, till it reaches here, and then makes a full acceleration using the gravity over here to reach the goal over here. Okay, so this is kind of a classical control sort of an environment. Here, the action space and the observation space, we'll discuss what it is, but this is how the environment looks like. Okay. Okay. So here, if I go to the GitHub page, which is the mountaincar.py GitHub page, so this is the entire environment which is coded. I'm simply doing gym.make, so I don't need to care what goes inside. But it's a good idea. It's a good practice to know what all is happening inside. Okay. So here, the observation is it's a two tuple. Okay, it's a continuous observation. First is the position of the car along the x-axis. So since we are only concerned with the movement of the car along the x-axis, at each time frame I need to know what is the position of the car along the x-axis. Okay, it's between minus infinity to plus infinity, and the unit it will give me a position. Second is I need to know the velocity of the car, which also lies between minus infinity to infinity, and in the end returns me a position, which is the velocity of the car. Okay, and the action space is three discrete deterministic actions, which is 0 means accelerate to the left, gives you a position. 1 means do not accelerate, do nothing. And 2 means accelerate to the right. So you have three actions: do nothing, accelerate to the left, accelerate to the right, or accelerate or decelerate. Okay. So you are trying to move towards the flag. Okay. The transition dynamics is given an action, the car follows the following transition dynamics. So it's velocity at time t plus 1 is velocity at time t plus whatever the acceleration you took times force minus cos times 3 position t into acceleration. So, okay, so it's defining the transition dynamics of the car. So, it's a simple motion model, how what the car follows. And the goal is to reach the flag placed on the top of the hill as quickly as possible. As such, the agent is penalized with a reward of -1 for each time step. It is not at the goal. Okay. The starting position is the car is assigned a uniform random value between this value for the starting position, and the starting velocity of the car is always 0. The episode ends in either of the following things. First is the position of the car is greater than or equal to point 0.5. That means the goal position on top of the hill. Second is the length of the episode is 200. So if it goes beyond 200, then also you stop the episode. Okay, so this is how the environment is defined. So I simply go here and I do envgym.make. So env contains all the information about the mountain car example with the observation space, the action space, the motion model of the car, the reward function, the initialization information. It's a class in itself. Okay. So we'll see in detail what each of this thing means. So first we look at the observation and the action space. Okay. Recording is we look at the observation and the action space. Okay. So first observation space is simply env dot observation underscore space, and the action space is simply env under dot action dot space. Okay. And if I print this, yeah, I think clear about it. Yeah, correct. So I have the observation space, I have the action space. So the observation space is basically a continuous variable here. Okay. So I'm looking at the position and the velocity, right? So my position is between -1.2 to minus 0.07. So this is the limit. Okay, so this is the lower limit of the position, minus 1.2, and this is the upper limit of the position. So this box specifies the lower limit of the two variables, and these specifies the upper limit, right? And the action space is a discrete quantity, which is a number between 0, 1, and 2. So that's why it's a discrete 3, right? So you have two different kinds of data for the observation space and the action space. One is something known as a box. Okay, so if I could just write type env dot observation space. So what I'll get is this is a gym dot spaces dot box dot box. So this is a box kind of a data type wherein each variable here takes a continuous value. Okay, and the continuous value is between this to this point. Okay, this is constricted between these 2 points, but it will always return a continuous value. Okay, and similarly, if I just look at the action space observation, sorry, the action space D type, so it's a discrete dot discrete. So if I, so what I'll do is, since I've defined my OBS space, okay, so my OBS space, I just simply do OBS space dot sample. So I'll get one instance of or one element from the observation space. Okay, when I do dot sample, I'm picking up one sample, and that sample lies between these 2 points. So this is the lower bound, this is the upper bound. It has to lie between these 2 points. Okay, if I do it again, I'll get some other thing, and let's say I do this 10 times. Okay, so I do for, okay, I have printed 10 instances of the, I have picked 10 samples from the observation space, and this is how they look. Okay, and similarly, if I do the same for the action space, yeah. So this is the action space, right? One means don't accelerate, zero is accelerate to the left, two is accelerate to the right. So these are just the 10 instances of me picking actions at random from the action space. Okay, I'm simply sampling. Now we look at the initialization aspect of it. Okay, first is we look at, so first I import from matplotlib plt. First I do the resetting of the environment. So when I do reset, that means the initialization condition is invoked. All the environment must be in its initial state. What was the initial state? We said that the car must lie between some portion which is at the bottom of the hill, right? And the velocity is zero. There are certain initialization conditions. When I call the env.reset function, the initial uh, condition or the initial observation of the environment is invoked. Okay, and that particular thing is called over here. So when I do OBS is env.reset, I'll get the state value, which is the initial state. So my OBS contains the state variable, which is the state is the position and the velocity. Or more specifically, it's the initial position and the initial velocity. Okay. Next, what I do is I sample a random action from the entire state space. So this is what I had done here also. I sample something from the action space. So I did env.actionspace.sample. So this will give me a random action. And next, what I do is I take the particular action. I take the action in the environment. Like I take the sampled action, simulate the dynamics, get the next state. Whatever I get, these are the data I have. Okay. So when I call the env.step function with that random action, it takes a step in the environment, does the simulation, and returns me the new observation. So I had the old observation. From this, I get new observation, the reward. Then the information if that condition is based on Boolean condition. So if it is true, the code will terminate after that step. If this false, you continue to do that. Okay. So you continue to do that. Okay. And eventually you have the new observation, the reward done, and info. Info basically contains any extraneous information you want to pass. So it's kind of a dictionary, which is empty for now, but you can pass certain information that you need for further computation. So it's a dictionary variable to pass ahead information. So now I print the new observation is new OBS. So the print statement here gives me the initial observation. Then after one random action, what will be my new observation? Okay, so if I run this, so I get my initial observation was this was my position, this was my initial velocity. Then after taking one instance of the action, so this was my velocity and this was my new position. Okay. So my env function or my env class, the mountain car class, not mountain car, any gym environment class contains these two things. One is the reset function, which we defined above. So this function resets the environment to its initial state and returns the observation of the environment corresponding to the initial state. This is what we did. So when I call env.reset, that I'll call it as my initial observation. Okay. Similarly, step function. What it does is this function takes an environment which leads to the environment transition to a new state. You can try to think of it as an MDP, and it's like you have a current state, you take a particular actions. What next state you go to based on the transition dynamics, whatever is present in the environment, based on that, you get your new state. Okay. And the reset function here returns four things. Okay. Sorry, not the reset, it's the step function, right? It's the step function. The step function here returns four things. Because if I do nb.step, I get four things. One is observation, which is the observation of the state of the environment, which I denoted by the variable new OBS. The reward that you can get from the environment after executing the action that was given as input to the step function. So this is the small reward. Okay. So it's the immediate reward that you get on taking one particular step. Second is the done condition, whether the episode has been terminated. If true, you may need to end the simulation or reset the environment to restart the episode. Okay. Next is info. This provides additional information depending on the environment, such as number of lives left or general information that may be conducive in debugging. Okay. So these are the that you have. Okay. Next, what I'll do is, so I have done the same thing here, right? Yeah, it's the same thing. So now there is another set of function known as the env.render. So what env.render does is it gives me a snapshot of what the environment looks like. So it's kind of a it's for visualization purposes. So it gives a snapshot of what the environment looks like because everything here is happening in the code itself, right? So if you want to know at each time step how the environment looks like or how the environment looks like in the simulation, so the render function contains that particular information. Okay, so if you remember when I define my gym.make, so this is my mountain car V0 and my render mode, I have either RGB array or I have human. So if I define it as human, so it is a more natural way of some more natural way of looking at the render part. But since I'm using a Colab notebook, I'll get particular error. Okay, which is cannot call env render before calling if this isn't okay. I should call env.reset. That's right. See, if I call env.reset, I say that no available video device. Okay, so if I run it on my PC, probably it should run, but the human mode doesn't run on the Colab notebook. So that's why I had to set it to RGB array. So it's giving me an image at each time step. Okay, I run this. I get what I was getting earlier, and if I do this, so what I get is a RGB array, right? So it's an RGB image containing the pixel value of each. In it contains the RGB pixel value for each particular point in the environment. And if I look at the shape, uh, yeah. So if I look at the shape, this is how the shape looks like. So it's a screen of size 400 cross 600 pixel, comma 3, meaning the RG and B pixel value. Okay. And finally, we call the env.close, so it closes the environment. Okay. And here, since we could only see numbers here, if you want to see it as a plot, so what I do is I put env.render into a variable called env.screen, and then I simply do plt.mshow of env.screen. So if I run this, I get a snapshot, okay, a beautiful snapshot of what the value looks like. Okay, so this is like in centimeters, this is defined. So if I reach somewhere zero point 0.6, if I reach around 600 meters, then it is said that I have reached the flag. Okay, so this is the snapshot of how it looks like. Right? Now, one would also like to look like what can you do? How can you control the values of the gem environment, right? So you have import time. You have from TQDM import TQDM. Okay. So this number of steps tells me how many number of steps you want to run the agent for. So for one episode, how many steps you would like to take. So you typically don't want a step or an episode to run infinitely long. Okay, so you tend to cut it off at some point. So if the goal is not found after this many steps, you say, okay, stop. You're clearly doing something wrong. You restart the episode. Okay. So this num steps define the length of an episode. It's the capital T value when we look at the time horizon, right? And then OBS is simply env.reset. Here, what I do is, so I'm running a for loop, which is from 1 to 1500. So I've used a function called TQDM. Okay, so this is, I'll tell what it does. So what we do is, first you take a random action, but you can do something more intelligent. Okay, because the entire course we have been looking at, it's the way we choose an action, right? So we studied the entire RL problem to know how the action selection looks like. So for the epsilon VD, we did the uh, epsilon times argmax of q function, or you did np.random action. Okay, so that's one way when you do epsilon greedy. When you do something like dqn, so that you look at the q update rule and then do the argmax, select the action, right? So for now we take random actions, but you can do something more intelligent. Okay, so this action is whatever is my intelligent agent or whatever is my RL function that is giving me. So to the RL model, I pass the observation and it returns me an action. But since I don't have an RL function right now, I'll take a random action, which is env.actionspace.sample. Okay. Then I apply the action. So I do env.step for that particular action. Okay. And I get OBS reward done and the info part. Okay. And then I click on, I call the env.render function. Then I do time.sweep. So I wait a bit before the next frame, unless you want to see a crazy fast video. So I want to give a pause to the frame. Okay. But since we don't look at the frame over here, so this shouldn't matter right now. And then, so this done part, it's a Boolean variable. Right? It's either true or false. True indicates that the episode is completed. You terminate the episode. Otherwise, you continue. So it's a check. Okay. If done is true, then you'd call env.reset. Otherwise, you just continue doing the step. Okay. And similarly, you also have a break here, right? So you know that if episode is done, you come outside the loop, okay? But let's say we don't do that here. But that's usually a good thing. But okay, I'll just put it. Okay. So if episode is complete beforehand, you break the loop and you come outside. Okay. This is based on the done condition, and afterwards you do env.close. So if I run this, okay, so this TQDM function gives me a nice widget kind of a thing, right? So I know how much of the loop is completed or how much is still going on. Okay, so now tells me that okay, I have completed 1500 steps. Since I can't look at the env dot render, why? Because I don't have a video uh, available device. But okay, I'll show you some examples. Okay, how it works. Okay, yeah. So this we say, okay, look in the upper bound of the environment observation, the lower bound of the environment observation, which is simply env observation space dot and env dot observation space dot low. Okay, so this gives me the upper and the lower bound for the observation space. Similar space, not the name. See, just copy paste. Yeah. So we okay, my network is not stable. So I think my internet is running fine. I can open it. Can you still hear me? Okay, I'll continue. Fine. So yeah, so when I do env.step, I'm putting an action. Okay, so this action is either some value because I'm looking at the mountain car example. So what I have three actions: 0, 1, and 2. So if I do env.action 2, which is accelerate to the right, I'll print it works. And if I put something else, it shouldn't work. Okay, it should throw an error. So if I run this, see, for the first case it works. For the second case, it says that this action 4 is invalid because uh, in the definition of the action space, I have defined it as a discrete tree, right? And lastly, this is how the full code looks like. So you have the action observation space, you have the action space, you have the env reset, and all these things. Right? So this is a simple code for controlling the elements of a gym environment. We'll naturally go into details of how it works. Okay, but this is just a simple example. So let's see. So we'll look at two examples of different environments. One is called Frozen Lake version 1 and one is called Taxi version 3. Okay. So in this code, you will code from scratch your first RL agent playing Frozen Lake using Q learning. Okay. So So this is how the taxi world looks like. Okay, so this is something we had discussed in the last stuff. So you have RGBY, passengers appear randomly. Okay, and the destination also occurs randomly. You have to pick the passenger, move, make them reach the goal. Similarly, in the frozen lake environment, you have uh, some traversable regions. Okay, and these holes you don't want to fall into the hole. If you fall into the hole, the game is over, and you have to reach the goal. And because you're moving on a slippery ice surface, there is a chance of you slipping. Okay, so if you take an action downwards, there is a probability you will slip to the left or to the slipperiness. So in this notebook, you be able to use gem library, be able to code from scratch a QLearn agent. And this is what we're do. So QLearn is what? An internal memory, so a value table kind of a method. A Q table, okay, that contains a Q table which contains all the state action pair values. Given a state action, a queue value will search into the queue table to give its corresponding value. So for state value, you make a query to the queue table and you get the corresponding queue value. So after the training is done, you have an optimal queue function. So an optimal queue table, because you constantly change the values of the queue values in the queue table, right? And if we have an optimal queue function, we have an optimal policy since we know for each state what is the best action to take, right? So my optimal policy pi star s is simply the argmax of u star s, right? So finding an optimal value function leads to having an optimal policy. So this is a link between the value and the policy, what we have looked at in the classes so far. And but in the beginning, our Q table is useless since it gives arbitrary values for each state action pair. Most of the time, we initialize Q table to zero. But as we will explore and update, it will give us better and better approximation. Right? So this is how the approximation looks like. Right? This is the pseudocode for the Q learning part. Okay. So this is the pseudocode. You can take a look at this. And share this. Copy link for Q learning. Okay. This is done. I'll start closing the links. Okay. Yeah. So since I don't have a virtual display, I'll just delete this. I don't have a virtual capture display. I can install all the gym things. Also, this is I'm installing all the Python dependencies. Okay. I'm not sure if this will run. Okay, so let's see how this looks like. It will take some time. Okay, let's see. Okay, so I've imported all the Python library functions. We are ready to code a Q learning algorithm. So for Frozen Lake, which is non-slippery version. So when I do env dot uh, gym dot make, I should put the Frozen Lake variables, right, including the map thing and the is slippery. So I should first do Frozen Lake v1. Okay, next I have map name. I'll do a simple 4x4. And lastly, I do is slippery is. So I let's say initialize with false. I don't need this. Okay, so this is running. Yeah, so this is the solution. Okay, so this should have been hidden. Right. But okay, so I just did this. So this is what the environment looks like. Okay, so you have once you do env.reset, you get the observation space, which is the env observation space, and you sample an observation. So I do this. Okay, so this is the observation space, which is discrete comma 16. Why? You see with observation that observation is a value representing the agent's current position as current row into a number of rows plus the current column. So where the row and the column start at zero. For example, in this 4 cross 4 map, the goal position can be calculated as here it is 3 into 4 plus 3. It's like this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. 0 to 3, 4 to 7, 8 to 11, and 12 to 15. Okay. So it's like I'm giving it a number. So you are moving like this. Okay. The number of possible observations is dependent on the size of the map. So for example, a 4 cross 4 map has 16 possible observations. For an 8 cross 8 map, you have 64 possible observations. So, for instance, this is what state 0 looks like. Okay, so this is the initial state. This is how the state 0 looks like. It tells you the current position of the agent, right? So, if state is 0, that means the agent is present here. Similarly, you have action space. So, your action space is 4. You just move up, down, left, right. When I do action space sample, I get a value. So action space is basically a set of all possible actions that the agent can take. It's discrete with 4 actions available, which is go left, go down, go right, and go up. Right. The reward function is if you reach the goal, you get a +1. If you reach the hole, you get 0. If you reach frozen, you get 0. Everywhere else, you get a reward of 0. Only if you reach the goal, you get a reward of +1. It's a very simplistic reward function. Right? So what you do is you create and initialize the queue table. This is again the algorithm for queue learning. So initialize queue table, you need to know how many rows and how many columns to use. We need to know what the action space and the observation space are, right? So OpenAI Gem provides a way to do that, which is env.actionspace.n, env.observationspace.n. So I just simply put this here. So I just put env.observationspace.n. So this gives me the state space. And simply if I do env.actionspace.n, it gives me the action space. So if I run this, I get, okay, there are 16 possible states and there are 4 possible actions, right? Let's create a queue table of size. So state space cross action space and initialize each value at 0 using np.zeros. So I need to do np.zeros state space, comma, action space. Okay. So queue table is basically a table, right? Which for each corresponding state, you have a corresponding action. State space. Then this. Okay. And finally, so this is the function that def initialize queue table. If I run this queue table frozen lake, what I should get if I print queue table frozen lake, let me know if my net is stable or not. Okay, okay. Okay, so it's zeros, right? So I have a 16 cross 4 table, which is all initialized to 0. And this is the, yeah, so this is the solution to what I just wrote. Okay. And then you define the epsilon greedy. Epsilon greedy is the policy that handles exploration exploitation trade-off. So you know the epsilon greedy algorithm. This is the representation. Okay, so this is the epsilon greedy thing. Okay, so you randomly generate a number between 0 and 1. How do you do that? You do np dot random dot random. That's what you get. Np dot random dot random. Yeah, you get a random number between 0 and 1. If that number is greater than epsilon, you do np.argmax, right? You do np.argmax of Q table, right? Q table corresponding to that state. State. Else exploration. How do you do exploration? You do np dot random dot random between 0 to 4. Okay. I hope I'm correct here. Let's check. Okay. Light change. For each state, I do this, and I can simply use np dot action space dot sum. Okay. Okay. And then you define the PD policy. We have all the steps here. Now take the action with the highest state action value, right? How do you do that? You do np dot argmax Q table state, right? Okay. That's correct. Then you define the habit parameters for training. So you train for 10,000 episodes. Your learning rate is zero point 0.7. You evaluate it for 100 test episodes. Your environment ID is frozen like P1, similar to the above. Max steps is 99, gamma is 0.95. You define a seed for the evaluation. This is how the mm, exploration parameters you decay it. Okay. You start with epsilon 1, you decay it with exponentially with the lambda value of 0.0005, very small value. Eventually, it should reach 0.05, right? You have defined all the training parameters, all the evaluation parameters. Yeah, this is the training loop, right? So you have number of training episodes, min, epsilon, max, epsilon, decay, everything is present. For each this thing, you reduce the epsilon because we need less and less exploration, which is min epsilon plus max minus min into np dot exp minus decay episode. Okay, so this is your exponential decay of the epsilon you're doing. So your state is env dot reset. Step is 0. Choose the action AT using epsilon greedy policy. What is the epsilon greedy policy? So you have defined, right? The epsilon greedy policy over here. This you just call this function here because eventually what you are getting is the action AT, right? So copy this here. I hope I'm right. This is simply nb dot depth of that particular right for that particular action, and this is the update rule. Okay, it's kill table state action plus gamma times p dot max of yeah q table of q state which is f right comma whatever action you get minus learning rate. I think I was doing correct. This is the epsilon greedy step. And just this, this, whatever this is. Yeah. And finally, I train the Q learning agent. Okay. So this is trained. Okay. Then this is how the Q table looks like after training it. This is initially it was zero. Now it looks something like this. Now you want to define the evaluation method. You want to see how the evaluation looks like. Right. So you have for each episode, you run it for how many number of episodes you want to evaluate. Set the seed. You now once you have the Q table, you simply do the argmax. Okay, you don't need to explore now. Once you have the Q max, you have the Q table. You simply do np.argmax of the Q state, and then you take a step with that particular action. Whatever reward you get, you add it to the total reward. If done, you break, then your state becomes new state. Whatever episode you have generated, you add it. This is the mean reward and the standard deviation of the reward. Okay. So evaluate function gives you an evaluation. What is the mean and the standard deviation of the rewards you are getting? And then normally you should have a mean reward of one. Okay. It is relatively easy since the state space is really small. What you can do is try with replacing the slippery version, but we want to simplify the problem. Okay. So this is how it looks. So my mean reward is one and my standard deviation is zero. Okay. Mean reward is one, which should be the case, right? Because it's saying that for all the 100 steps, I am reaching the goal. That means I'm getting a reward of one. So this is learned well because it's a deterministic environment. If I make it to be slightly complicated, like I have slipperiness, so there might be some cases where it fails. Okay, so there is a small standard deviation which is invoked, but okay. Similarly, you do it for the taxi V3 environment. Okay, it's the same problem. Uh, I have all the codes prepared, right? So there are 500 discrete space. Okay, so since there are 25 taxi positions, five possible location of the passengers, and four destination locations. So it's 25 cross 5 cross 4. 5 cross 4 is 20. 20% here is 500. Similarly, action spaces up, down, left, right. Okay. Okay, but in addition, you have two more actions: just pick up passenger and drop off passenger. So these are non-primitive actions. Do you remember what we did in the last lecture, right? And the reward function is -1 per step. Otherwise, other reward is triggered. +10 for delivering a passage. -10 for executing pick up and drop actions illegally. Okay. So you create your queue table for the taxi, which is 500 cross 6 table. You define the hyperparameters similar to what you have been using. So you train it for 25,000 episodes, learning rate is 0.5, N eval is 100. You have defined some evaluation seeds, and then your environment ID is taxi V3. You each episode is for 99 time steps, gamma is 0.95. This is the exploration parameters, right? And then I'll simply train the Q learning agent. Uh, okay. Yeah. Once this is trained, this is how it should look. Okay. Okay. And finally, we should also look at the evaluation, right? So I just copy this, paste it below here. Okay, okay, by taxi. Yeah. So here uh, I get a mean reward of 7.52 and a standard deviation of plus minus 2.67. Okay. So here there are cases where it fails. Okay, because sometimes I might pick up or drop off passengers illegally and stuff like that. And eventually we have the result for QLearn. Okay. Once this is done, maybe next thing what we can do is so far what I have been doing is using some repository which is already defined in the OpenAI gym. We have looked at the mountain car example. We have looked at the taxi version 3. We have looked at the frozen lake version 3. What if we would like to create our own custom gym environment? Okay, this is also possible. You need to just look at certain variables in mind and you can create your own custom gym environment. So to start with, so I'll do something from scratch. We'll create a gym environment similar to frozen lake problem from scratch. Okay, I'm not referring to any uh, pre-existing repo code which is available on GitHub. Okay, so we'll try to create it from scratch. How do you do? You just try to first define all the Python dependencies. Okay, import numpy, np, import matplotlib.pyplot as plt. Yeah, from tqdm import tqdm. Okay, this is import necessary libraries. Okay. We'll put stuff in it as in when we need it, right? So first, it will take some time to connect. Yes. Yeah, and of course we should do import gym, right? Because we want to use gym environment eventually. And here we'll say that my actions are left is 0, right is sorry, it's left, down, right, and up. Okay, why? Because we are moving counterclockwise. Okay, or is it clockwise? It's a counterclockwise motion. It's 0, 1, 2, 3. Okay, so this is the this. I'll write it here only. Possible actions, right? And then since I'm using OpenAI Gym, I'll first create a class which I'll call as grid environment. Here, I'll make a call to the super class, which is gym.env. Okay. And then I'll first call the def init function. Okay, this is the class constructor, which has the self function. I'll say my grid is none. I haven't passed any grid information yet. Then I'll start defining stuff. Okay, so I'll say self dot grid size is equal to grid dot shape 0. Then the define self dot area is self dot grid size cross self dot grid size. Okay. Next, I say self dot last action is done. And then I say self. I'll define the number of rows and number of columns. Okay, self dot n row and n col is the number of row, number of column to be grid dot shape. Okay, simply. What else? What else? Mhm. So in this grid, first I should define a start and goal page. I say let's say self dot per row or self dot current column is equal to np dot where. So let's say I'm giving a grid by default, okay, with the start and the goal position. I do comma t type is equal to c. Then np dot where my grid double equal to my the value s. Okay, that will be my start position, and this equal to the zero value. Okay. Similarly, I define it for the goal. So instead of per row, I put goal row. Copy, paste. And here also I put goal. Copy, paste, paste, and instead of S, this should be goal. Okay. What else? I think this should be it, right. Finally, say my self dot state is simply I should calculate the distance to the goal. Okay. At each time, I should know what is the distance that I have to cover to reach the goal, which is which value. It's np dot. Okay, let's not take the square root. I just take the absolute value. Okay, so I do absolute value of self dot goal row minus self dot current row plus same thing copied for the column. So what I'm doing is I'm directly taking the Manhattan distance instead of taking the Euclidean distance. Okay, then self dot direction. So I need to know which direction to the goal, which direction my goal is at. Okay. So I need to define a function to call my direction. So let's say call it self dot get direction. Okay. So this I have to define later. So finally, what I have is I have np dot array having self dot direction. So these are my states, comma self dot first distance, comma self dot direction, right? And eventually I define my observation space, which is first my observation is distance, right? So distance is a value which has to be gym dot spaces dot box. My distance value goes from no, since this is Manhattan, so I don't even need to define it as a box. I can define it as a discrete quantity. So let's say the max possible distance is whatever is the area, right? So whatever is the size of the grid, I just multiply it with two number of rows plus number of columns, right? So that means that's the max possible Manhattan distance I can take, okay? Which is if I start from one diagonally opposite corner, I go to the other diagonally opposite corner. This is the max value it can take. Similarly, my action is gym dot spaces dot discrete. This is four, right? I have four possible actions, right? I have to define the get direction first, okay? So we have to keep that in mind. Next, we call the reset function. Does the reset function look? I think it's the uh, same thing, right? I mean, we can more or less copy all things here and put this. That means, except we don't have the grid, right? Self dot grid everywhere. Here also self dot grid. My grid is fixed. Self dot grid is fixed. Everything else remains as it is. In fact, all these quantities still remain fixed. Only the current row and current column fixed changes, right? So wherever there is grid, I just replace it by self dot grid. So I make it a class variable invariably. And where else? Here, change here. Yeah. Once this is done, you do return self dot state. So it contains all the information for the return function, right? And then finally, you do def step, which takes the action as argument, right? What happens in def step? If action double equal to zero, okay? I should mention that what are the actions. I had defined it above, but for clarity's sake, I should write it here. Left down is one, right is two, and up is three. We are moving in the anti-clockwise direction. If this is true, I say my new current column I increase by one. Sorry, if action is to move left, I self dot current column I decrease by one. Okay. Or whichever is right. Should I can't decrease it beyond zero, right? So that's a condition I have to keep in mind. Elif action double equal to one, which is to move right, move down. So the new current row remains the same, no change to that. Okay. New current, if I move down, then I'm increasing the row by one. Okay. So my new current row is self dot current row plus one. And here I put a max term, right? Max with self dot n row. And which is same as this, just that one. Here this will be max, self dot n call, and just say ls action is three. Then this thing comes here. Well, let's say I don't define direction now. Okay, I'll make life more simpler. I don't want to complicate things now. So my state contains only the distance to the goal. Okay, there is no direction at each time step. I only get how much distance I still have to cover, and based on that, I take corresponding actions. Right? Distance is and I remove direction component totally. What else? Yeah, so this is the dynamics. Okay, so I have defined the new current column, the new current row, and stuff like that. And I define my Manhattan old first, which was absolute of this quantity, right? Self dot distance. So the Manhattan old and my Manhattan new would be this quantity replaced by the new variable we have, right? My old state was my old state was this quantity with the old Manhattan distance. Okay. Similarly, my new state would be my new Manhattan distance. Uh, then I define new letter as self dot grid new current row, comma, new current column, whatever is the value. And I say if new letter double equal to b comma h, I'll simply say my new state is equal to old state, and whatever is the new state, I'll just define the distance, right, which is the value I get corresponding to the new state. And the reward is 1 if new letter double equal to b of g, else 0. Okay, I get a reward of 1 only if I reach the goal, otherwise 0. And what is the done condition here? Done condition is also simple, right? I simply just look at if this is true, and that done is true. I have the new state value. I simply return new state reward, comma done, comma info. Okay. Similarly, you can define your render function, but for now, I'll put it as a pass because otherwise the class will move ahead. I have to also look at stuff. Okay, how to define the render. Okay, so what I've done is I have created a custom gym environment wherein I am taking the grid as a parameter. My grid size is grid.shape 0. Area is grid size plus grid size. Uh, I have defined the number of rows and number of columns from the grid. Wherever it's S, okay, so I should first define the environment. Right? Then only I can explain. Yeah, I should say the grid is, first of all, it's a 4 cross 4 grid. This, comma, this. Okay, so this is the starting position. This is F. This is F. This is, okay, let me copy paste this thing here. Okay, so it's a simple environment. S implies start position, G implies goal, F implies the regions which are free. Okay, and H implies there are holes. Okay, so I have defined 3H over here. Okay, so if you fall into a hole, you die. Episode gets reset. Okay, so this is how the grid looks. So what I do is I pass it as an argument as a parameter to the class constructor. I define the grid size area. Wherever there is S, I define it as my current row and current column. Okay, agent starts from position S. Okay, goal is wherever there is G. Distances, I am taking the absolute distance between the goal row and the column row plus goal column and the current column, which is I'm taking the Manhattan distance right now. Okay, my state is simply the distance that I want to minimize each time. Each time step, the agent is getting how much farther away I am from the goal. Okay, observation space is a discrete quantity. I have taken it discrete because it's a Manhattan distance, right? So I'm trying to uh, put a check. Okay, so Manhattan distance at max can be self.n call plus self.n row, which is if I start from a diagonally opposite corner and I want to move to the diagonally other side, so this is the maximum possible distance I can travel in a grid. Okay, action space is up, down, left, right. The reset function is again simply reinitializing the environment. Wherever there is S, I put it as my current column. I reinitialize my distance. My state is again the distance. Step function is something interesting. So if I want to take a left step, I decrease my column by one. But since I don't want my column to be less than zero, I put a min condition. If it is less than zero, I put a bound on zero. I can't go there. Okay. So if I'm at the leftmost column and I want to move left, I can't go there. I'm constrained by that. Okay. So the column changes. New current row remains same as the current row. So for downward also, I change the row value, column value. So this is the motion dynamics. The old Manhattan distance is the original self dot distance. The new Manhattan distance is whatever gold row minus row, new current column, stuff like that. And you have the old state, which is Manhattan old. You have the new state. My new letter is checking. Okay, if self dot grade at that particular point, what is the value? So is it H? Is it F? S or G? If new letter is H, that means if there is a wall, then I don't go there. Okay. So it's like I don't fall in. It's like not a hole, but a wall. H is like a wall. So if I hit a wall, I don't go there. I stay at the current position. So my new state remains the same as the old state. And then my distance is whatever value I have, I put it into the distance. Reward is one if I reach the goal, else it is zero. The episode continues. Okay. This is how it looks. And finally, if I were to, I'll define the environment, right? So my environment is grid env, which has grid is equal to grid. Okay. So I'm passing a grid parameter. I hope this is correct. Grid environment is not defined. Okay, I should run this first. And then run this. Yeah, this is fine. Then I do env dot reset. I should get the initial position. So it's array comma 6, right? That means from here, the distance is 3 plus 3. I should, so that's why I'm getting a value of 6 over there, right? Finally, if I do, let's see, render function, right? Maybe I should try. Okay, what if I just put the grid value, right? I just put self dot grid, print self dot grid. So whenever I call the render function, I do this. So now I just do take some random action, right? So I say act is env dot action space dot sample. Okay. So I should get some ACT, some action, which is random. And from here, I should get new state, comma reward, or rather, I should simply just print it now. env dot step ACT. Uh, Index 4 is out of bound for axis 1 with size 4. Okay. Yeah, should be minus. Wherever there is max, it should be minus 1. And somewhere there should be a min. Action 3 is move up. Up to mean I should decrease the column by 1 and make this 0. Okay, let's see. Yeah, now I'm getting the output. So if I take a random action, what was the random action? So let's print that again. First print act. So I start from the initial position. My random action is 0. 0 means I want to go left. Uh, Something's wrong. Okay. It's it's showing a distance of 7. New state is 7, which shouldn't be the case. Okay. That means I moved left whereas I shouldn't move left. Okay, let's say I remove. Let's say I call this. Let's not confuse us with Manhattan. I say this is new distance. Self distance is new distance. If it is h, shouldn't move. Okay. Left means 0, right? So current. Makes sense. Yeah, I think now it works. Okay. So if I take action 3, which is 3 means to go up. Okay. So if I try to go up, I won't be able to go up. Okay. Because again, if I take action 3, I can't go up. Now it's action 2. Okay. Action 2 means I should go to the right. So if I go to the right, so now it's 1, 2, 3. Okay. Yeah. I think something is getting misprinted somewhere, but more or less the code is working. Okay. Some small changes, heuristic level changes one needs to do. So what I do is I just go here. I go for I take random 5 random actions and I print env dot reset at every time step, and then I call env dot render. Okay, let's not take this out. Hmm, okay. So what I'll do is uh, I'll call some random action first, which is env dot action space dot sample. Okay, then I get new state, comma reward, comma done, comma info is equal to env dot step for that particular action. And I just call env dot render. Okay, so it's like I take 6 random actions. I should also look at what action I took. In fact, I should create a dictionary, right? So it's easier. So I action it, which is 0 means left, 1 means down, 2 means right, and 3 means up. Okay, I just print the action dict of this. Yeah, it doesn't show anything about the agent here. How do I show the agent? Okay, what I can do is here, wherever the agent is present, is self dot current, rather I should I create a dummy grid. Create dummy grid is equal to self dot grid dot copy. Dummy is equal to grid dot copy. Yeah. So I'll copy the grid value here. Here also in dummy grid self dot current row comma self dot current column is B comma A. Okay, so that means wherever the agent is present, I should show an A over there. Okay, so that things become clearer. Let's see. Hmm. Agent is here. It tried to go left. It stayed here. Again, it tried to go left. It stayed here. So I think it all 5 times tried to move left, but it stayed in the same place. Okay. I, again. Okay. 4 times it tried to go left. It stayed there. One time it tried to go down. Somehow it couldn't go down. I have to check why. Okay, I mean, maybe I can leave this as an exercise. Okay, so I have some more stuff still to cover. You guys can start debugging it to know how it works. So it will also become clearer to you guys. Okay, later. Custom gym environment. Okay, this is done. So yeah, I can close this now. Close this now. Now I'll just show two simple implementation for DQN and DDPG. You can look at it. Uh, just I'll give a brief overview. I won't go into the details of how DQN or DDPG works. So DQN works for a discrete action space kind of a thing. So we have covered this in class. DDPG is a deterministic variant wherein you apply DQN, you modify DQN so as to apply it for a continuous environment. Okay. So if you want more details, you should go to this site called OpenAI Spinning Up. So it's called spinningup.openai.com. So you have all the latest state of the art deep learning algorithm along with proper documentation, references, algorithm, conceptual knowledge, as well as implementation details. Okay, so one should definitely visit this site. It's called Spinning Up AI. Okay, so I'll start with DQN. Okay, so I won't run the code. Maybe it will take some time. Okay, let's try. Let's try running this. So here I have set up a virtual display. I put all things in the collab file. It will take some time. Let's wait. I think similarly I can start this simultaneously, okay, for DDPG. Here we'll be looking at a cart pole environment. Okay, I should define the environment before. Okay, so for DDPG, we are looking at something known as the cart pole environment. What happens in cart pole environment is you have a cart wherein you're balancing a pole. The objective is you are moving along the x-axis, left or right, and the pole should remain in an upright position. Okay, it shouldn't fall down. Action space is discrete too, which is move left, move right. Observation space is what is observation space? Observation space is the position of the cart, which is from minus 4.8 to plus 4.8. Velocity of the cart, which can be from minus infinity to plus infinity. The pole angle, minus 24 degree to plus 24 degree. And the pole's angular velocity. These four quantities, actions are push left, push right. Okay. Reward is goal is to keep pole upright. Reward of plus one for every time step taken, including termination step. The reward threshold is 475. Okay. Starting state is all observations are assigned uniform random value in this space itself. The episode ends if pole angle is greater than plus minus 12 degree. Card position is greater than plus minus 2.4. If episode length is more than 500. Okay. So for this, you just call gym.make card pole viewer, right? Let's see if it is done. Yeah. So I install all the necessary packages. So for DQN, you have something called as a replay buffer, right? So you store all the experiences into a buffer. So it's a class which creates a replay buffer, which has two methods. One is store, whatever experience I have. If I call the store function, it stores it into the replay buffer. Sample batch means if I make a call to sample something from the replay buffer, it does that thing for me. We are going to use a simple neural network architecture with three fully connected layers in two nonlinear functions, which is ReLU. With input dimension 128, 128, output dimension. This is how the network looks. Okay, so it's a PyTorch implementation. And a DQN agent. So I have a class called DQN agent, which has these methods and what it does. So the first method, select action, selects action from the input space. Step normally takes a step and returns the response of the environment. Compute DQN loss, returns the DQN loss, which is the MSC loss, okay, in DQN. Update model updates the model by gradient descent. Target hard update makes a hard update from local to target model. Train does the training part, test does the testing part, and plot simply plots how the training progresses. Okay, so go through this, read these things. I'll paste it here. Since there is a time crunch, I'm just trying to rush through it. This is the DQN implementation. I just run this class. I install Pygame. I define my environment ID and the environment as gym.make cartpole v1. Okay, simply, I set a random seed. I define the seed. I initialize. Oh, okay, I'll ignore this button. Okay, so this is the memory size, batch size, target update, the epsilon decay. So what happens in target decay is that, sorry, what happens in target update is that uh, you have a target, you have a current estimate, right? You want to update the current estimate more often than the target update. So you freeze the target update for a certain number of time. Otherwise, you are simply dealing with a non-stationary problem, right? So you fix the target update, not you fix the target network. You continue to modify the uh, whatever estimate network that you have. And after 100 time step, you transfer all the learned weights, the model weights to the target network. Okay, so you update the target based on the current estimate. That's what it does. And this is the training part. Okay, so I'm training it for 10,000 time step. Hmm. Where many values to unpack expected 4. Step function, right? Yeah, in 4. Really, if I go to the step function, so there what they are returning is the array, a reward, done, something called false, and this help. Okay, so small change I have to make. I should go here, step, this is info. Before that, I have to put a dash. Okay, hopefully this works. So let's see this. Where is this? Yeah, I think it's the. Uh, did it not get updated? No. Yeah, let's see. Hopefully this should run. Okay, one more place apparently. Here, here. This is done. This is done. Ah, let's see. Hopefully this should run now. There is this self is test. Before this, there is some error being thrown. This is fine. This is fine. This is also fine. What is the issue then? Yeah, I think there has been some update with the earlier uh, from the earlier version. I'll just show the recording. Okay, so maybe you can try debugging. This I had a run before the OpenAI had made changes to their environment, but yeah, this is after 10,000 episodes. This is how it looks. Okay, for DQ1, and similarly, this is an implementation for DDPG. Go here. This is DDPG implementation. So here we look at some environment known as a pendulum environment, wherein what you do is you want to keep, there is a pendulum which is swinging. You want to keep it in the upright position for as long as possible. Okay. Similar to what we have done before, you define the replay buffer, you define the module, replay buffer, whatever is the actor critic method for DDPG. This is a summary. You take a look here. Okay. I think right now, uh, since I had implemented this, there has been some changes made to the OpenAI codes. I also have to debug it. So take a look, see if you are able to debug, play around with it, see if you can make sense out of it. But yeah, this was all I had to cover for today. Let me know if you have any other questions. Uh, I think this is a good time to stop now. Okay, I have shared more, like, a lot of informations today. Uh, this is probably a good time to stop. You have a lot of material to look at. So yeah, let me know if you have any further questions. Otherwise, we can stop this session. Okay. So this is the final session for this semester. If you have any further questions, which is beyond the course content, feel free to reach out to me. My contact details are available. Okay. So yeah, that's it. It's 7:52. I think it's a good time to stop now. So thank you for attending. Uh, it was I had a great time teaching this course, and hopefully we'll meet next semester with some other course with new faces. Okay. So thank you. I'll stop the session. Okay. Thank you. Bye. Okay, I'll wait for 2 minutes and then I'll stop the recording. Okay. Okay, I'll stop the recording.